Hello, everyone. I'd like to share some practical example of how we use Cesium for Unreal to visualize civil engineering project. In this presentation, I will talk through several topics. Why the surrounding spatial context is so important. How we visualize observation data, and how we simulate events. Today, I'd like to begin this presentation by explaining an overview of Nippon Koei's activities, and then followed by an introduction to various data visualization. ID&D Holdings is a global development consulting firm. We have worked in over 160 countries, helping to build social infrastructures. Our project includes social capital development, urban planning, and energy development. Nippon Koei is a key member of our group. First of all, let me introduce how we using Unreal Engine. We use it as tool to visualize infrastructure development to help everyone understand the infrastructure development contents well. For example, we create a park design based on the sketch made by children and visualize using Unreal Engine. Another case is we create digital visualization for Sony spatial reality displays, which does not require any glass to view 3D scenes. In this case, we create the contents by using a 3D city model called Plato, which is developed by Japanese government. And we also create digital visualization for the threat of tsunami to help people to get immediate response in case of an emergency. And to make this experience accessibility any device, we use cloud streaming technologies. So today's main topics is how we are using Cesium for Unreal. And I'd like to talk about the importance of the surrounding environment. The surrounding environment is crucial in planning and construction. It's always come up when building a consensus among stakeholders. They say that we understand that what building proposed. But how about accessibility? It is in harmony. What kind of impact? Then exactly, we use visualization to help answer these kind of questions. We need to create 3D models, not only the design site itself, but also of surrounding areas. We generate these surrounding data using point cloud scans and photogrammetries. But here is the challenge. Depending on the case, creating the surrounding 3D environment can take just as much time and effort as modeling the design site itself. So in this case, we did not use Cesium ion. This example shows UAV data from collapse of the Aso Bridge, which occurred during Kumamoto earthquake in April 2016. We visualized the post-collapse condition using Unreal Engine. And this is visualization of Restore Bridge. At the time, Unreal Engine support train up to 64 square kilometers. However, that 3 wasn't enough to fully represent the entire surrounding areas. So we only create the terrain that was visible from key viewpoint. And now we have a cesium ion. Creating the 3D model of design object usually takes anywhere from 20 to 100 hours. Building the surrounding environment with a cesium ion is take another 20 to 40 hours. But now, with cesium ion, we can get it in under an hour. That is huge time saver. So here is the basic workflows. First, we add the cesium ion asset. Then using cesium georeference, we set the geographic location for origin point in Unreal Engine. Next, we make sure the cesium ion data does not show up inside the design area. To do that, we define an exclusion zone using cesium cartographic polygons, and then apply it cesium polygon raster overlay. Finally, we set the existing structure and the time of day using cesium sun sky. That is just a few simple steps. Now let me show you an actual example we create. That one is about riverbank area development, where we design a waterside public space. For the design area, we use BIM data. For the bridge and nearby structure, we use point cloud data captured by TLS. And for the overall terrain, we use cesium world terrain from cesium ion. Okay.
Thank you so much, Sato-san. So for now, I will take over the presentation. And my name is Sidhu, and I am the researcher and architect of the Nippon Koei. So, okay. So up to this point, everything we have shown has been typically use case for Cesium for area. Now, this is a bit of the different use case for Cesium for area. This content shows 2 years of earthquake activities across Japan. Take a look. It is pretty shocking, right? So many earthquakes happen in just a short time. That's exactly why we need to stay prepared, not just physically, but mentally too. We created this content as a reminder to always be aware and ready for the earthquakes. So, okay, let me explain how we visualize the location of the earthquake epicenter. First, we converted the seismic data into CSV format. Each data point represents an epicenter, and we assign colors based on depth. So next, we use Sony spatial reality display to present the data in 3D. So does anyone familiar about the Sony spatial reality display? Okay, good. So Sony spatial reality display is the display which doesn't need any glasses or any device to view the 3D. So it just literally popping up the 3D view. So it's difficult to show the 3D model in the regular display. So this is the platform we are showing our contents. Okay. So that's made possible through the Sony dedicated plugin, which allows us to display the point data in a highly immersive way. So there is a plugin called the Sony Spatial Reality Display plugin as the plugin for the Unreal Engine. So we use this plugin to make this contents. When we show this to experts in geoscience and disaster prevention, their reaction was very positive. And they said, That's great. And at the same time, they also gave us several additional requests and suggestions for improvement, which we are now considering to improving our contents. So to display the seafloor topography, we found that the Cesium wall bathymetry could be the good solution. However, showing the earthquake epicenter in a time series format was more difficult. So we explored the different options and ended up using Niagara area engine particle system. So first we prepare a text file with the particle spawn position, time, and magnitude. Then we set each particle to appear based on its x, y, height, magnitude, and time. To make it GPU friendly, we converted the data into the texture inside area. Finally, we read this texture to control when and where each particle appears and how big it is. So this is the result of our work. We use the data from actual earthquakes. A magnitude 7.1 quake that occurred off the coast of the Miyazaki, Japan in August 2024. The visualization shows the seismic activity before and after the event, so using the real data from the time period. Yeah, so that big green is an earthquake, big earthquake occurred. Okay. Okay, this is an example of this example uses output from the IRIC, a hydraulic analysis tool. What's interesting is that we are displaying this simulation result in area engine without changing the original file format. One expert can easily understand the simulation data. It can be hard for the non-experts to interpret the data. So by showing it in a more realistic real-world style, people can better understand how river might change after the modification period. We are also experimenting with the flow line visualization to make the data even more intuitive, not just realistic, but easy to understand in the right way. And once again, Cesium plays a key role. It clearly shows the exact location of the scene. Yeah, this is the flow of the river. Okay. So this is our final example, a visualization of the landslide simulation. We're using a Cesium ion here as well to show where the simulation is happening in the real world. The points you see represent the vertex of the terrain match, which deform over time as landslide progress. So we also apply the texture model to make the changes easier to see and understand. Okay, that's it. So for the summary, so using Cesium ions has made our workflow much more efficient. It streamlines access to the geospatial data and helps saves a lot of time. The rich spatial data sets available through Cesium ion also make it easier to interpret complex scientific simulations. And with the Cesium for area, we can express data in many different visual styles and support multiple devices, making it easier for more people to understand what's going on. So yes, Cesium ion and Cesium for area have become essential tools in our work. And we will keep pushing forward and creating visualizations that are clear, intuitive, and easy to understand. So that concludes our presentation. And thank you so much for your attention. I'm happy to take any questions you may have. Thank you so much.